Hey, geometry students. We are moving on from transformations for a little bit, and we're going to talk about some other concepts. Today we're going to talk about tessellations, which is kind of a fun thing to do. What is a tessellation exactly? Well, it is a shape or multiple shapes that cover a plane, so a two-dimensional space with no gaps or overlap. Right? So, I'm not saying it could be any shape, but there's lots of different shapes that tessellate, and even when combined with multiple shapes, even more things tessellate. So, first type of question, do the following shapes tessellate? Well, a rectangle. Does a rectangle, is it a repeatable shape that would cover a two-dimensional space with no gaps or overlaps? And as you can see here as I draw, that's the case. I mean, think of a brick wall. A brick wall is an excellent example of rectangles tessellating. There's no gaps, there's no overlaps, and it covers that two-dimensional space. Check. It works. A regular decagon. That's kind of weird. I have a tough time drawing decagons, especially regular ones, so let's just come back to that in a second. Equilateral triangle. Those are easier to draw. Does an equilateral triangle tessellate? Well, let's see here. If I kind of just draw some of these out, will this cover the plane? Well, I think it's pretty clear to see that, the more of these that I draw, there's no gaps, there's no overlaps, I'm just going to cover the plane. So yes, an equilateral triangle will work. So going back to the regular decagon, how could we find out? Well, let's see. Maybe we could try some other shapes and see if we could find some patterns. How about a square? Square is an equilateral shape. So is it true that all equilateral, or not equal, but regular shapes tessellate? Well, the square certainly does. An equilateral triangle certainly does. What about a pentagon? A regular pentagon? It'd be kind of like a soccer ball. There's no gaps or overlaps in a soccer ball. Okay. What about this one? Feels kind of weird. It just doesn't look right. If you can think back to the warm-up, you don't have the warm-up if all you're watching is the video, but in the warm-up we found the measures of one interior angle in regular polygons. And so in a regular pentagon, we would say, okay, the sum of the interior angles would be 3 times 180, which of course is 540. But if we want to find one of those angles, we would divide both sides, or divide all that by 5, and we get 108. So each of these angles inside a regular pentagon would have to be 108. So this would be 108, and this would be 108, and this would be 108. But notice what should all three of these add up to? It should add up to 360, because that's a circle. But 3 times 108 is not 360, and so a regular pentagon does not tessellate. Can we apply this kind of new knowledge to a regular decagon? Well, it's going to be real tough for me to actually draw multiple decagons and see how many I could fit in there. Maybe I could look for further relationships. In an equilateral triangle, each one of these would be 60, and I have 6 of them, and, well, 6 times 6 is 360. 60 is a multiple, or not a multiple, but it's a factor of 360. Here, each of these are 90, And 90 times 4 is 360. 90 is also a factor of 360. So ultimately what it comes down to is one interior angle going to be a multiple of 360? Well, I suppose we could find out for sure here with the regular decagon. The sum of the interiors would be 8 times 180, and that would be 1,440. Divide that by 10 because we've got 10 sides, and, well, that means each angle would be 144 degrees. Is 144 a multiple, or not a multiple, a factor of 360? No. And so a regular decagon does not tessellate. So good questions there. A couple other things that you might be required to do with tessellations. Example 2, change a quadrilateral to make a tessellation. So this is kind of what your project is going to be about. Your problem solving also does or uses this today. So here's what you're going to do. You're going to make a quadrilateral, or whatever they tell you to make. And to make it kind of a cool quadrilateral, if you just Google image tessellations or like M.C. Escher tessellations, you find all sorts of cool things like that. But what you do is you essentially just take one side out, and whatever you do to that side, you kind of do the opposite to the other. So, my shape at this point would look something like this. And because what I did to one side, I did to the other side, I can continue this as a tessellation. And it would look, something like this. Okay? So that is kind of the idea behind what M.C. Escher does to make his cool, fancy tessellations, and what you're going to do for yours. Another thing that you're going to perhaps have to do is draw a tessellation using like two different shapes. And so like here's an example. I guess I already drew it for you, of a regular hexagon and a regular triangle, an equilateral triangle, kind of mixed together to tessellate. All right, well, that's tessellations. Next time we meet, we will be talking about symmetry.